Hello guys, Cyprien from FEA for All, and in today's tutorial we'll have a look at OpenTurns, which is a module of Salome that will allow you to do various kind of probabilistic modeling, so including reliability, sensitivity analysis using methods such as Monte Carlo and other kinds of methods. You can do few kinds of data analysis. You can do probabilistic modeling. Well, there are a lot of tools in this, and we'll have a look at that together. So today's tutorial has been provided by a reader of the blog, Fernando Oleo Blanco. Thank you very much for making this video. So you will find a full text version of the content of this video on the blog. So if you want to follow that step by step and do it in your own Salome using OpenTurns module, you can go on the blog and follow also the text version. And before we go into the video of the tutorial, let me tell you what this video will be about. First of all, Fernando will show you how to create a beam like that into Salome Geom, how to mesh it, and how to use Code Aster to apply a load on one side and fix the other side. And then he will show you how to define some variables and make this analysis parametric by using the Young's modulus and the force on the other side as a parameter, and how to put that into OpenTurns. And once this model will be into OpenTurns, Fernando will show you how to make the load and the Young's modulus variables vary and change according to certain probabilistic distributions, such as a normal distribution, and how to do all this analysis at the same time using OpenTurn and Code Aster integration linkage together. And how you can, the various way you'll be able to look at the results. Results calculated with the Monte Carlo method, and which will give you some probabilistic indicators such as the mean, the standard deviation, the coefficient of variation, the skewness, and also different kind of minimum and variable and maximum of the variable calculated. And you'll be able to look at different kind of plots like this, or the table plots, or different kind of cobweb plots, all this. So without any more explanation, let's go into this tutorial.
Firstly, I would like to thank Cyprien for letting me upload a video to his channel, and I would also thank everybody who watches this video and gets something out of it. So, as the video title may suggest, we are going to be focusing on how to interface Code Aster and OpenTurns to do uncertainty quantification or sensibility analysis. For this purpose, I will be using Salome Meca version 2019. However, the 2018 version also allows and has an automatic export of a Code Aster case into OpenTurns. It is important that you notice that this is not the OpenTurns module is not available for the Windows version, so you won't be able to follow this if you're using the Windows installation of Salome Meca. Another point that's important for you to know, I won't be focusing too much in the geometry, meshing, and basic case setting in Code Aster, mainly because that's not the goal of the video. The goal of the video is to focus on the specifics of Code Aster that need to be done in order to export it to OpenTurns, and then do a simple and quick demonstration in OpenTurns. Therefore, I will be going quite fast during the geometry meshing and basic case preparation. So if you feel overwhelmed or you think I'm going too fast, please feel free to pause the video and follow it at your own pace. So, as always, we are going to set the geometry in order to generate our case. It's going to be very simple. The goal of this video is not to focus on a complex simulation. Therefore, we are just going to create a simple beam. In order to do that, let's create a box. I'm going to be using the international metric system, the SI units, better said, and therefore everything will be in meters, Pascal, and Newton. So let's give this some somewhat realistic measurements. Dx is going to be 0.3, dy it's going to be 12 meters, and dz it's going to be half a meter. Apply and close. With the box selected, make sure that you click on the fit selection button, which is this lens and a cube under it, so that it zooms automatically into our object. Then let's create some geometry groups. Right click on the box, create group. And let's create the load phase. Well, first let's create the fixed phase. Select the phase that's at the origin, add it, and create the fixed phase. Let's create now the loading phase. Select the opposite phase of the beam, add it. And then we are going to create two edge groups, mainly to help us with the meshing. We're going to create the DX group. You can choose whichever edge is in the DX direction, add it, and DZ direction, whichever one you may need. Apply and close. Before we continue, let's save the case. Now let's get into the meshing section of the video. Select the box, fit to selection, and now with the box selected, let's create a mesh. Mesh type hexahedral, automatic hexadralization, hopefully I pronounce it somewhat correctly, and let's give it 100 different segments. Apply and close. With the mesh 1 selected, let's create two subgroups, or submesh, sorry. From the geometry, we are going to select the X. It automatically sees that we are selecting an edge and gives us the 1D option. In algorithm, we are going to give it a wire discretization. In hypothesis, we are going to add a number of segments, which is going to be 10. Okay, and finally, in additional hypothesis, let's say we want that same hypothesis propagated to all the opposite edges. Apply. Let's do the exact same thing with the DZ of edge group. Salome automatically fills the same hypothesis that we had just created, so we just hit apply and close. Let's compute the mesh. Well, first let's select the mesh 1 and compute the mesh. Here we can see the mesh that it has created. Now, with mesh 1 selected, let's create two geometry groups. Those will be our fixed phase and the loading phase. Create group. We're going to create group of faces. Group from geometry. Direct geometry selection. Let's select our fixed group. And let's name this group fixed. Apply. Let's call this next group load. And let's select the load phase. Apply and close. If you would like to see those two, just click on the eye icons and you will see them. We will come back later to do another group, but for the time being, let's just make sure that we have a successfully running case, and we will add a final group that we will be using to do the uncertainty quantification. Let's save the case. Let's go into Code Aster. Well, actually, Code Aster study. And let's set a very basic simulation case. Once again, I won't be explaining everything with great detail, since this is not the goal of the video. Add a stage. And with our stage 1, let's start creating a very basic simulation. With image. Mesh 1 and format met. Model definition. Assign finite element. Finite element. Everywhere, phenomenon mechanic, although you can just pick whichever one you want for your case. In this example, we will be doing a mechanical simulation, and we are going to be using the simple 3D solver. Okay. In materials, let's define a material. Linear isotropic. Young modulus e to the 9 and Poisson ratio 0.3. Okay. And let's call this material steel. Let's assign the material to our beam, to our mesh. Now let's create two boundary conditions which are going to be our fixed phase and our load phase. So assign mechanical condition, load, sorry, and then fixed. Enforce degree of freedoms. Group of elements. Fixed. And select the list one and encastre. Hopefully I didn't butcher the French pronunciation there. And okay, now let's create the load. Assign mechanical load. And we're going to scroll down till we get to force phase. Group of elements. Load. And let's give it, I don't know, minus 737 kilonewtons down in the Z direction. And now in analysis, we want to do an static mechanical analysis. In the material field mat, which is our assigned material, our model, and loads, we want to add both loads, the fixed load and the load 0 load. Now that we have created our simulation case, let's see if it works correctly. In order to do that, let's click in History View, add our stage, and click Run. The case runs to completion, which means it is set up correctly and now we can focus on the specifics on how to get it to work with OpenTurns. In order to do that, we are going to, or the case that we are going to see in this video, it's a very simple case, and we are going to do a very basic uncertainty quantification analysis of how much deflection the beam suffers depending on the load and depending on its Geom modulus. In order to do that, we are going to add a node group. So if we go back to the meshing tab, let's open the mesh 1, and select it. With the mesh 1 selected, we are going to create a, well, actually first, let's change the view so that we can correctly see the end point of the beam where the load is going to be applied. With the mesh 1 selected, let's create a group. It's going to be a node group, and we are going to call it node 1. Select Enable Manual Selection and select whichever node you want from the lower section of the beam. Add it. Oh, sorry, I didn't select it correctly. Add it and apply and close. Let's go back to Code Aster. Case view. And let's save the case. Now, in order to generate a Code Aster case which can be used in OpenTurns, we need to export that data in a format, the result data of our simulation, in a format that OpenTurns will be able to interpret. To do that, we are going to create a table. In order to create a table, we need two different functions. The first one is in post-processing, and it's called post_relef_t. This function will allow us to extract data from our simulation. In action, let's add one, and we are going to extract a result from the wrestling simulation, our wrestling analysis. In operation, we are going to do a simple extraction. From that extraction is going to happen from a group of nodes. That is why we created our node group, which is just going to be this simple dot over here. And we are going to, we need to select what do we want to extract from that node. I'm going to extract one of its results, and it's going to be the DC displacement. We are going to see how much it will drop after the load and the Geom modulus is applied. We can give it a name. Let's call it displacement. And the name of the field, it's going to be a displacement field, depl. Click OK. Now we have created our table. In order to output this table, we need to create an output table. That is done with, in the section output, import table, which I suppose means imprint table. Click on it. In the table field, we want our table selected. Since we only have one, it has already been selected automatically for us. And we need to create a file name. So click on those three dots and let's add a file. And name it in whichever way you want. But let's add, you have to add the MPI extension to the file. So I'm going to call it dset table dot mpy. Let's save it. In order to see what is being output, click on the format and leave it at tableau. This is not correct and this won't work with OpenTurns. However, we are first going to run a simple simulation to see the information that's been output into that table. It is also very important that you name your parameter. It's not required when we are running the tableau option, but it will be very important if we are running an OpenTurns simulation. And we are going to call our parameter dset. Let's click OK. And now save the file. Let's go into history view, select our current case, add it, and run it again. It has run to completion. Now let's go into our save folder where we saved our case. And now you should see a file named in whichever way you named your output table. Let's open it. Select whichever text editor you may want and look into it. As you can see, we can see the name of the parameter that we have given it and the actual displacement, well, the actual parameter that we wanted to output. In this case, it's the dset displacement, -5 millimeters. Okay, great. Now we see that everything is working. Let's go back into our case view. Select our output table and change the format from tableau to numpy. This is the only format that works with OpenTurns. So it's very important that you select this one. And I want to repeat myself. It is also very important that you name your parameter. Otherwise, the export function will tell you that you need to give it a name. Click OK and save it. In order to export a Code Aster case into OpenTurns, we just have to go up into our stage 1 case, select it, and right-click it. Sorry, not into our stage 1, into our current case. Select it and click on it. Here you can see our export to OpenTurns. Let's click on it. The export function, the export dialog will tell us that we are still missing one thing. Here you can see it's giving us a warning. No Python variable found. You must add one or more Python variables in a graphical stage of your study. This means that if you have a pre-made case, for example, one that you created a long time ago, the parameters that you're using within your case need to be turned into variables. These variables are going to be the case input variables in OpenTurns. In our case, we are going to change two parameters, the Geom modulus and the force that's going to be applied. So if we select in our case the steel material, double click on it, go into the linear isotropic section that we created earlier, and let's change this number, which is just a simple number, and let's change it into a variable. Add a variable. If you didn't notice, I click on the right symbol to go from a simple number to a variable input. Add a variable. Let's name this Geom, and we need to give it an expression. This expression doesn't need to be a mathematical formula. A simple number will do. We'll just give it what we had earlier. Okay. Okay. We're going to do the exact same process with the false. So, under boundary conditions and load, let's select our load. Scroll down to where we selected it earlier in false phase. And now in FC false, let's change the number into a variable. We click on the drop-down menu and click on Add a variable. Name it false. And the expression, whichever number you may prefer. Let's say 37 Newton. Okay. Let's save the case one final time. Let's scroll up into our current case, right-click, and export to OpenTurns. Here, in the output NumPy file, it has automatically detected that we are creating an output, a table output in the format of NumPy. If you did not create a output with a NumPy as a NumPy table, it will warn you that you need to create one. Here in the variables section, we can see the two variables that we have created. These are going to be the input variables that our OpenTurns case is going to work with. Select whichever ones that you will want to export as an OpenTurns input variable. In our case, we are going to select both, false and Geom. And we can finally click OK. And now we are automatically launched into OpenTurns, where our case has been automatically exported. Let's save the case. The screen that you are seeing right now is the definition screen. This is where our case is being defined. The most important bit in this screen is this JAX model data file. If we click on Edit, it will open the Python script that OpenTurns is receiving from our Code Aster simulation. I won't be explaining it right now, maybe in another video. Here in the Definition tab, in Inputs, we can see our two variables, false and Geom, with their preset values that we had added. In the Outputs, we can see the dset output variable. And the value right now is unknown, since it doesn't know which is the correct result, since we have yet not run an OpenTurns simulation for these inputs. Let's evaluate it. What we'll do is that OpenTurns will start now its own engine and will run the simulation that we have created in Code Aster. And it is going to use a force value of 37 kilonewtons and 210 gigapascals for the Geom modulus. And with those two values, it's going to give us the output value. As we can see, it's the exact same one we had earlier, nearly 5 millimeters down. Now, in order to do a simple OpenTurns simulation, let it be sensibility or uncertainty quantification, let's go into our current case in the left panel. Here you can see the OpenTurns graphical user interface. If you click in Model Definition, you will be evaluation point that we are going to run. And here you can change the number of parallel evaluations that you may want to do at any given time. These are parallel evaluations within OpenTurns, not the number of parallel of the different calls that may be used by Code Aster. If you go into the Advanced Parameters tab, here you can see some extra information. This information was automatically extracted from our OpenTurns case, from our Code Aster configuration case. So, for example, we had a limit, maximum duration limit of 15 minutes within Code Aster. This time refers not to the maximum time that OpenTurns may run the simulation, but the maximum time that each Code Aster simulation is allowed to run for. And then files and directories, we may see, we may get, well, I may explain them in a bit more detail in another video. These are usually, these are generated for you automatically when you export the case. Let's go back into a quick configuration and let's hit run. This run should end up with an error. I will explain you why in a moment once we get to see it. Okay, here you can see it's giving us an error that a previous result already exists. Since we had already evaluated this point, 37 kilonewtons and Geom modulus of 210 gigapascals, that simulation, that earlier simulation, has already created an output directory for those two exact points. This simulation tried to create those exact 2 points, but it is detecting that they already exist, and it's giving us an error. If you would like to rerun a previously done point, you have to go to the working directory that OpenTurns generated. In my case, is Salome workdir Fernando blah 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 blah. And this is the important bit. Run param minus 37,210 gigapascals. This is the directory that we need to delete if you want to repeat a simulation. So if we go to this directory, Salome workdir, this one, which is the current one, and you need to enable hidden directories. If you cannot see this .run param directory, you need to enable hidden directories. Once you enable hidden directories, you will see this this directory which starts with a dot, which means that is a hidden one. If you double click on it, well, you can right click on it and delete it if you want, or I would encourage you to take a look into it, especially into the results parametric. Here you have the results that, well, the output files that Code Aster generally generates. For example, the output simulation file. And you may take a look at it if you would want to understand how it is working, and especially if a simulation within OpenTurns fails, it is quite useful to take a look into what Code Aster is generating. For now, I'm not going to delete this directory, but you may want. Also, if you may want to get a closer look at what's the exact results that are being generated, those results for that specific point will be within these types of directory, which are always named run param with the names, or well, the points that are being used for that simulation. Okay, let's go back into our current case. Here we can do some screen optimization, design of experiments, and the final bit we are going to do in this video is a probabilistic model definition. Here we need to define the statistical definition of our input variables. Let's select both false and young. Now, here you can select whichever distribution you may want. For both, I'm going to select a normal distribution. Here in the configuration panel for that very definition, distribution, you can select which parameters are going to be used. Some of them have several types of definitions. Let's leave them as they are. It's not very realistic, but it will show what we want to do. If you want some more advanced features or a bit of a refinement, you may also add some dependence between those input variables. We are not going to do that here. Once the probabilistic model definition has been set up, let's go back into our current case. Here we can see that the sensitivity analysis, central tendency, and limited state definition have been highlighted. That means we can now run them if we want. For this demonstration, we are going to do a central tendency simulation. Click on it. Leave the method as Monte Carlo and make sure that our output is selected. Continue. Now, we need to select some parameters that we may want to refine. The accuracy of our simulation, the maximum time we are going to let our simulation run for, and this refers to the OpenTurns simulation, not the Code Aster one. Or a maximum number of calls, a maximum number of points that we want to be generated. I'm going to select a maximum time and I'm going to leave it for 30 minutes. Now you may want to leave it for less or you may want to leave it for more. The more time you let this run, the more points that will be generated. So keep that in mind. Now let's click on finish. Here, once again, we have the configuration panel for our central tendency problem. I'm not going to change anything. I'm just going to launch the simulation as is right now. And I will let it run till completion. That means 30 minutes. After 30 minutes of simulation in my case, you will be automatically presented with this new screen. In this new screen, you will find the results that were generated during all those simulations and the final analysis. Here you have different tabs: the summary tab, PDF, CDF, box plots, dependence, table, cobweb plot, plot matrix, scatter plot, parameters, and model. In the summary tab, you may find the different variables, the output one in our case, and the two inputs. And you will be presented with their different analysis. So their means, standard deviations, confidence interval, coefficient of variation, skewness, etc. Also with the minimum and maximum, and their relation to the inputs, which is always very important to look at. PDF, CDF. Under the table tab, you will find the different inputs and the output that they generated, also the different runs. You can take a look at them, you can sort them by value, and you can export the table if you want. In the cobweb plot, you can see the different inputs and output relations of the different simulations. In the plot matrix, if you have some points selected under the cobweb plot, they will be highlighted under the plot matrix. And you can change the different views depending on which portion of the matrix you click on. To finish this video, we here have the scatter plot. Under the left panel, you may change under the graph settings, you may change the title, the different parameters that are being shown, and the relationships. For example, so let's select Geom. We can also change their scale, their limits, and also export it. This finishes up this video. I hope you learned something from it. Once again, I would like to repeat that this video's goal was to show you the general process on how to get a Code Aster simulation into OpenTurns. This was definitely not the most effective way of how to simulate an uncertainty quantification problem, but you can extract the different steps that we've given in this video to apply them to your own cases. And finally, I would really like to thank Cyprien for letting me upload one video to his channel, with the hopes that a lot of you will get something out of it. So thank you very much, and thank you, Cyprien.